Further, large irrigation channels can also be used for inland navigation, and moreover, like on the banks of the channels, you can also grow trees, which surely will improve will increase afforestation in that particular place and also improve the oxygen levels in these places. Also, even though we have seen so many advantages of irrigation, there are some disadvantages of irrigation. Particularly, it increases the water pollution levels. Particularly when you are going to apply fertilizers for your crop growth, these fertilizers mixes with the water and seeps into the groundwater and thus pollutes the water. Further, it also induces dampness in the climate, which increases the breeding of the mosquitoes. Further, over irrigation may also lead to waterlogging and may reduce the crop yields to a greater extent. One important factor that one has to consider when taking up the irrigation projects is like the revenue to the government, the revenue return to the government is very less. For example, the cost of investment in constructing the irrigation schemes, which includes canals, dams, reservoirs, gates, all those things is much costly or much greater when compared to the profit obtained by the government or by the individual persons when they do irrigation. You can just see, like for example, if you are constructing the Polavaram project, the amount of money that is invested is much greater when compared to the returns that the government is going to get through the farmers. So irrigation can be of different types. So basically there are two types, one is surface irrigation and subsurface irrigation. So surface irrigation means the water moves on the ground and goes into the plants. And subsurface irrigation, water comes from underneath the soil and then reaches the root zone of the plants. So surface irrigation can be further classified into flow irrigation and lift irrigation. And lift flow irrigation can be classified into perennial irrigation and flood irrigation. So we'll see what are these in detail. So as I said, flow irrigation is a classification of surface irrigation. Here the water is available at a higher level and it is supplied to the lower level by the action of gravity. So water moves from a higher point to a lower point, where at the lower point there is no any water, but at the higher point you have water. So you allow the water through canals to move from the higher level to the lower level through gravity. On the other hand, lift irrigation, when the water is lifted up by some mechanical means or manual means such as pumps, is known as lift irrigation. Further, the flow irrigation can be categorized into two kinds. One is perennial and flood irrigation. In perennial irrigation, there is always continuous supply of water throughout the year in order to meet the requirements of the crop. So the water can be directly taken from a river which is at a higher elevation to the field which is at lower elevation through some storage structures such as dams. On the other hand, flood irrigation, in this the soil is kept submerged thoroughly with flooded water. So once in a while you allow the water to move into the field and then immerse and then submerge the entire field with water, so that whatever water is required, the crop will take for that. So this kind of irrigation is occasional and it is not continuous. Whenever there is a water, you flood the field with water and then stop the flow of water into the fields. So subsurface irrigation, as I told, can be categorized into two types, natural or artificial. In subsurface irrigation, the water does not move on the soil surface, rather it does not even wet the soil surface. Rather it directly goes into the subsurface of the root zone. So natural subsurface irrigation is like leakage from the channels. You construct a small furrows in the field and you allow the water to move on to the field in the furrows. Then water will go to the root zone directly by percolation. On the other hand, when it's artificial, you artificially lay some pipes through which a drain is there, through which you allow the water to move, and from that you allow the plants will take the water through by the action of capillary effect. So these are the different types of irrigation that people generally practice all across the world. So there are different types of water distribution in the farms. So how do we distribute the water that is available for the plants on the field? So based on this, there can be different classifications. Number one, free flooding, border flooding, check flooding, basin flooding, sprinkler and furrow irrigation and drip irrigation. So in the case of free flooding, water is just allowed to move freely like a surface flow on to the farms. In the case of border, you create some borders, bunds all along the field, and you allow the water to stay there for some time, and then water will percolate or even it will be used by the plants. In the case of check flooding, you create small check dams where the water will stay there for some time. Whenever there is excess water, it overflows and then it moves on to the next field and so on and so forth. In the case of basin flooding, the depth of the field, it's a basin kind of a structure is created and water is allowed to stay there for a long time. For example, you can consider the rice or the paddy which is grown in our areas is an example of a basin flooding. And sprinkler flooding, you have water drips directly to the root zone. There is no any wastage of water due to evaporation. And in furrow irrigation, as I said earlier, like you create a small furrow kind of a thing in the fields, and water is allowed to move onto in the furrows, and the plants are grown on the top of or the banks of this furrow, so that water will enter to the plants through the effect of capillary. So more details about this particular different techniques of water distribution can be found in the book by Irrigation Engineering by S.K. Garg. So now coming to the main topic, every crop requires some amount of water for its growth, and that we call it as crop water requirement. So as we all know, we all require food, water for our growth. So similarly, crop also requires water in certain quantity for their growth during the entire period of its beginning to the end of the growth period. So if there is a regular rainfall during the entire crop period or the growth period, then there is no any need of irrigation. On the other hand, when there is irregular rainfall event that is happening, then we need to regulate the flow to the crops so that they can grow in an effective way. For example, in England, the geographical situation is like that. There is a regular flow, regular amount of rainfall falls all across the year, so that there is no any necessity for irrigation structures. On the other hand, in India, as we all know, the rainfall is highly varying, therefore it is important to have irrigation structures all across the country. So in order to define the crop water requirements, we need to understand certain basic terms that is called as crop period or base period. So it is a time between the first watering of the crop at the time of its sowing to its last watering before harvesting is called as base period or base of the crop or the crop period. So there is a slight difference between the crop period and the base period. So crop period actually denotes the starting point when you sow the crop. On the other hand, base period is the time of watering that you do. So even though the difference is very slight, in many of the places we use crop period or base period in a synonymous way. So generally base period or crop period is denoted by B, and it is having a unit of days. Now coming to the next topic, delta. So each crop requires a certain amount of water after a fixed interval of time. So the summation of the total water that is supplied from the beginning of the crop growth to the end of the crop growth is called as delta. So generally we use depth of water to denote delta, and delta as a unit of centimeter or millimeters. So for example, the crop period is 120 days, and every 10 days you are giving 10 centimeter of water. That means the total delta will be 120 centimeter. You can just take this in a simple example. If rice requires about 10 centimeter depth of water and the average interval of watering is 10 days, that means every 10 days you are going to supply 10 centimeter of water to the rice, and the crop period is 120 days, and find out delta. This is the question. So the water required at an interval of 10 days, the total number of watering or the frequency of watering is 120 divided by 10, that is equal to 12 times. So each time if you are giving 10 centimeter, the total delta, the total amount of water in depth is 120 centimeter. So these are some of the typical values of delta for different crops. Like delta for sugarcane is highest, like 120 centimeter, and delta for rice is 120 centimeter, tobacco is for 75 centimeter, wheat is 40 centimeter, and peas is 15 centimeter. So we can just see how so sugarcane and rice can be grown in places where you have excess water, and all other crops can be grown where water is less available. So now the third quantity that we are going to see is duty of water. So as the name suggests, it's a duty of water, like it is a relationship between the volume of water and the area of crop it matures. Suppose you have 1 meter cube per second of water is continuously flowing into the field, then how much amount of area that this particular water can irrigate. So that is the definition of duty. So it is defined as the number of hectares, please note it is number of hectares of land irrigated for full growth of a given crop by supply of 1 meter cube per second of water continuously during the base period of that particular crop. So continuously you are going to give 1 meter cube per second of water throughout the base period. If you supply this much amount of water, how much area can be irrigated, and that is called as duty. So there is a relationship between duty, delta and base period. So we will derive this relationship. So let the crop or the base period of the particular crop be denoted in B days, and let 1 cubic or 1 meter cube of water is applied for the field for B days. So the volume of water is 1 meter cube per second into B into 24 into 60 into 60. So why this 24 into 60 into 60? It is for converting the days into seconds. So we get the total volume of water that is being supplied is 86,400 into B meter cube. But by definition, D, what is D? D is duty of the water. 1 cubic meter of water supplied for B days matures D hectares of land. Yes, is it okay? Yeah. So it's going to irrigate D hectares of land. So the volume of water that is required by D hectares of land is D into 10 power 4 meter square. That is nothing but D hectares of land is nothing but D into 10 power 4 meter square. The total depth of water that you are supplying is V divided by area, that is nothing but 86,400 into B divided by D into 10 power 4. So that is going to be delta is equal to 8.64 into B divided by D in meters. So please note the B that you are going to substitute in this equation is in days and D is in hectares. If you change the unit, then accordingly this entire derivation has to be changed. So please note delta is equal to 8.64 B divided by D in meters. A simple problem. Find the delta for a crop when its duty is 864 hectares per cubic. On the field, the base period of this crop is 120 days. So it is a direct problem. Delta is equal to 8.64 B divided by D, where B is in days and D is in hectares. So 8.64 120 is days and 864 hectares per cubic. We are going to get 1.2 meters and delta is equal to 120 centimeters of water. So now the duty is going to be varying at different places. For example, a river is there and this river you are having a canal regulator. It is connected to a canal through a canal regulator, and there is a main canal and there is a branch canal and the distributor canal and there is a minor canal, and then from the minor canal it directly goes to the field. So a water that is getting diverted from the river has to cross through all these channels at different levels in order to come to the field where the farmer is irrigating the crops. Now as it is following this particular passage, there is loss of water due to evaporation and maybe due to percolation. So if you allow 100 meter cube per second of water at the river, what you may get at the field may be 70 meter cube per second of water. So what is happening to the remaining water? The remaining water is getting lost due to the losses, that is due to evaporation and percolation. So obviously the duty of the crop is going to change. It will keep on decreasing as we are moving from upstream to the downstream. So what are the factors affecting duty? The type of the crop. The type of the crop is going to affect your duty. If the crop is having more delta, then obviously your duty is going to be less. Duty and delta are inversely proportional. So similarly, climatic and seasons and amount of useful rainfall that is happening during the irrigation period, and what is the type of the soil. If the type of the soil is like clayey soil, then there will be no much percolation. If it is sandy soil, there will be loss of percolation. So obviously that duty is going to be reduced for sandy soils. So similarly, efficiency of the cultivation method. What is the method you are going to use for applying the water to the crops? So that also going to affect your duty. So for example, duty of certain crops, sugarcane is having 730 hectares per cubic, rice is having 775 hectares per cubic, and hot fodder is 2000 hectares per cubic. You can very clearly see that 1 cubic of water supplied for the base period B days can be used only to irrigate 730 hectares. On the other hand, if you use any other crop or fodder is like material used for feeding the cattle, you can cultivate 2000 hectares per cubic of water. So obviously sugarcane and rice are highly more water demanding crops. So as I said already, duty is inversely proportional to delta. If delta is more, then obviously duty will be less. If your delta is more, then duty will be less. So some of the crop seasons which we should know as we are doing this particular topic. So generally the crops can be classified as Kharif or Rabi crops. So Kharif crop is a crop that is grown generally between April to September. So you can also add plus or minus depending upon the areas. So some of the crops which have Kharif, which are grown in Kharif season are rice, bajra, maize, jowar and groundnuts. And Rabi is also called as a winter crop, generally grown between October and March. So wheat, barley, gram and linseed are the crops which are grown during the Rabi crop. So generally these crop seasons are only valid for North India because in South India we don't have generally a concept of winter season. There is no much it's called as winter season, but in general we also follow a similar kind of a cropping season is being followed in all across the country. Now there are other terms which we should know when we are talking about this irrigation. So one is called as core watering, K-O-R watering, core watering. So it is the first watering given to the crops is called as core watering. So the first time when you give water, as after some time they sown, it is called as core watering. So similarly another topic called as paleo irrigation. So paleo irrigation is nothing but sometimes when the soil is very dry, before the irrigation or sowing is start, the soil is very dry. In order to moisten the soil, you add some water to the land. So that addition of water, that irrigation, in order to reduce the dryness or increase the soil moisture, before sowing the seeds are called as paleo irrigation. Now coming to another concept, crop rotation. So crop rotation is a concept where you keep on rotating the crops which is grown in a given field or a given farm. So why it should be avoided? If the same crop is grown again and again, then what is going to happen is the soil is going to lose its fertility or the nutrients which is supportive for the particular crop. So obviously the plants will be deficient with that particular nutrients and they may not be able to yield properly. So in order to reduce this problem, you have to rotate the land with different crops so that different crops gives or takes certain nutrients to the soil or from the soil. So in general, the crop rotation helps in recuperation of the nutrients in the soil. So generally you can have a cash crop followed by a fodder crop, a gram, which can use for fixing the nitrogen which is lost during cash crop, and then again you can grow a cash crop. So that if the cycle follows, then obviously the soil health is maintained. So similar other examples of crop rotation are wheat, jowar, gram, rice, gram. So obviously the crop rotation increases the fertility of the soil, reduces the disease and reduces the number of insects that is attacking the plants during its growth, and also increases the yield of the crop. So crop rotation is one of the important practices recommended by the government agencies. So now coming to the concept of irrigation efficiency. So as we all know, efficiency is a term that is related to many aspects. So whenever there is something that is coming in to a system and that is going out of system, then we can define efficiency as what? Output divided by input. So we have studied efficiency of turbines, we have studied efficiency of pumps. So similarly we can also study or we can also define efficiency of irrigation systems as a whole. So as we already seen, there is some losses due to conveyance or due to evaporation or due to storage or due to application or different kinds of losses of water is happening. So obviously you can define efficiency at different stages of water as it moves from the river to the farm. So efficiency of water conveyance. So you have a canal starting and you have the canal ending. So when start point to end point there is some losses. So obviously you can define a efficiency for water conveyance. So eta C is defined as output divided by input into 100. So similarly water application. So you use different methods for water application to the crop. You can use a sprinkler, you can use a drip irrigation, or you can use a furrow irrigation. So depending upon how much amount of water you apply and how much amount of water actually reaches the root zone, that is defined by water application. So similarly water storage, you are storing the irrigation water maybe in a canal or in a dam or in a reservoir. So obviously there will be some losses due to evaporation, due to percolation. So you can also define water storage efficiency. So similarly water use efficiency, how much you apply at the beginning and how much is actually used by the plants, is water use efficiency. So you can define efficiency at different terms at different stages of application of irrigation. So a simple example, 1 cubic of water is pumped into a form distribution system. 0.8 cubic is actually delivered to a turnout 0.9 kilometer from the well. Compute the conveyance efficiency. So the water, when it's traveling a distance of 0.9 kilometer from the well, initially it was given only 1 cubic of water, but what it actually reached the field is 0.8 cubic. So the output is 0.8, the input is 1, so the efficiency is going to be 80%. Another simple example, a 10 cubic of water is delivered to a 32 hectare field for 4 hours. Soil probing after the irrigation indicates that 0.3 meters of water has been stored in the root zone. So what is the field application? So this particular problem talks about field application. So how much is the water that is applied by you? 10 cubic of water for a period of 4 hours. So 10 meter cube per second into 4 into 60 into 60. This is for converting hours into seconds. And what we are going to get is 1,44,000 meter cube. So the input that you are going to supply to the field is 1,44,000 meter cube. But what is actually observed in the field in the soil probing is 0.3 meters of water has been stored in the root zone. So the remaining all water has gone as percolation or as evaporation. So what is the total area? 32 hectares into 0.3 meters. So that will give us the total amount of volume of water that is getting stored in the root zone. So 32 into 10 power 4, in order to convert it to meter square, we have 32 into 10 power 4 into 0.3, that is going to be 96,000 meter cube. So the water application efficiency is again output divided by input into 100. The output is 96,000, input is 1,44,000, and into 100 we are going to get efficiency of 66.67%. So this is the example where we can see the application efficiency is around 67%. So now, how do we estimate the crop water requirement? How much amount of water a crop is required for its growth? So in chapter number 3 or 2, we already studied evaporation or evapotranspiration, which is also called as consumptive use, and we have studied different methods for estimating the consumptive use. Blaney-Criddle method, Penman-Monteith equation, and Thornthwaite equation. All those things we already studied how to calculate the evapotranspiration or consumptive use. Okay. So once you know the consumptive use of the plants, that the amount of water required by the plants, and you know the total effective rainfall that is actually happening in that particular area, then if you find the difference between the two, then you can know what is the consumptive irrigation requirement that you need to provide for the crops. For example, the consumptive use or the plants is 120 centimeter, for example, in the case of rice. For example, that particular area is experiencing only 70 centimeter of rainfall. So what is the remaining amount of water that you need to supply? 120 minus 70, that is 50 centimeter of water needs to be supplied to the crops. So now this is the crop water requirement. So now what we need to give to the crops in order to account for the losses. So net irrigation requirement is equal to consumptive use minus rainfall plus losses such as percolation, evaporation in canals or dams and reservoirs. So that will give us how much amount of water actually you have to give, so that only CU at least reaches the farm. So as I already explained, CU can be estimated different methods. using Blanik-Rudel method and Penman equation. So the simple equation which can be used is Blanik-Rudel equation. Cu is equal to K into P divided by 40 into 1.8 into T plus 32, where Cu is the consumptive use in centimeter, K is a crop factor which is going to be a function of the crop, and P is the percentage of annual daylight hours, and T is the temperature, mean monthly temperature in degree Celsius. So if you know these values, then you can easily calculate the consumptive use for the particular crop. So you can also see some examples of this particular thing in problems that we have solved in chapter number 2. Coming to the important topic of this particular chapter, soil moisture irrigation relationship. So even though we have already talked about this in unit number 2, but still in this context we need to define these definitions in a more clear way so that we will know how much is the amount of water that we need to give for the crops for growing. So let us consider a impermeable layer, and you can just consider the ground level here. So you can just see the crop root. This is the root zone that is going to a smaller depth. We are going to call it the root zone depth, and below the root zone depth we have intermediate zone, and below the intermediate zone we have the capillary zone. And this is the groundwater table that is there, and this is the water table. So anything above the water table is some amount of water is going to move into the soil because of capillary effect, and in this particular zone, the root zone, it is this particular depth in which the water is going to enter into the crops through the roots. So as I already explained, we need to understand two important topics. That is called as field capacity, the other one is called as a permanent wilting point. So field capacity, it is the moisture content or the water content or the percentage of water or water moisture that is there in the soil after free drainage has taken place for a sufficient period of maybe 2 to 5 days. So it is that water content which gets retained in the soil pores against the gravity. So the field capacity is consist of two parts. One is called as capillary water that is available to the plants. The other one is called as hygroscopic water that is not available to the plants. So field capacity is defined as a quantity of water which any soil can retain against gravity. It is expressed as the ratio of the weight of the water contained in the soil to the weight of the dry soil. So Fc is equal to weight of the water retained in a volume of the soil, in a given volume of the soil, divided by weight of the same volume of dry soil into 100, and that's what the definition says. So let us consider a small area of 1 meter square of soil and d meter depth of the root zone. So the depth of the root zone is d meter and the area that we are considering is 1 meter square. So the volume of the soil is going to be 1 into d, that is d meter cube. So the dry unit weight of the soil is represented as gamma d kilonewton per meter cube. Then the weight of the soil would be gamma d into 1, that is nothing but kilonewtons. Is it okay? So gamma d into d meter cube will give me gamma d into d kilonewtons. So if F is the field capacity, then according to definition, F is equal to weight of the water retained in the unit area of soil divided by what? Weight of the dry soil, that is nothing but gamma d into d. So therefore the weight of the water retained in the unit area of soil is equal to F into gamma d into d. So the volume of the water in the stored in unit area of the soil is nothing but what? F into gamma d into d divided by gamma w. So what I am just doing, I am just dividing it by the specific weight of water so that I can get the volume. So if I want to get the depth of water that is stored in that particular 1 meter square area, then I need to divide it by 1 meter square here. So the depth of the water that is stored in the root zone in the soil filling up to the field content is field capacity is nothing but gamma d divided by gamma w into F into d in meters. So if you know the field capacity in percentage, if you know the dry density of the soil, if you know the density, or if you know the specific weight of water, and if you know the depth of the root zone, then we can easily find out to what depth the water is actually stored in the root zone. So this is field capacity. Now coming to the permanent wilting point, it is the water content at which plants can no longer extract sufficient water for its growth. So at permanent wilting point also there is some amount of water that is there in the soil pores, but the soil plants cannot extract that water for its growth. So the available soil moisture or the available water that is there available for the growth of the plant is nothing but field capacity minus permanent wilting point. So generally all the available moisture is not available for the plants. Only 70 to 80% of the available moisture is readily available or easily extracted by the plants, and this is called as readily available moisture. So all the available moisture may not be used by the plants. Only 70 to 80% can be only used by the plants, and that is called as readily available moisture. Like this will become more clear like this. So let us assume the moisture content is plotted on y-axis and the time is plotted on x-axis. For example, the field capacity is at this level. You can just see field capacity moisture content. So the moisture content is being measured here, it is 0, and this is Fc, and this is Fc. Now this is the PWP or the permanent wilting point. So even though there is some amount of moisture that is there, but this is non-available hygroscopic water, and whatever is between Fc and PWP, that is called as the available moisture content or the capillary water. So now the entire water available moisture content is not actually available, only 70 to 80% is available. So therefore this is nothing but the 70 to 80% of the available, and this becomes the optimal moisture content. So what is actually available is readily available for the plant is this being this and this. So this is readily available moisture. So for the plants to grow, generally the moisture content in the soil should be between field capacity and the PWP. Generally it is not allowed to be depleted up to the wilting point, as it would result in the considerable fall in the crop yield. So we should never allow the water content to drop to the PWP, rather we should maintain at some water level above PWP, and that is called as the optimal moisture content. So the difference between the field capacity and the optimal moisture content is nothing but the readily available moisture. The optimal level of moisture up to which the soil moisture may be allowed to be depleted in the root zone without fall in the crop yield has to be worked out for every crop. So for some crop it can be at 70 to 80%, some crop it is 60%, some crop it is 50%. So that has to be worked out for different crops individually. So please be clear, this particular diagram is very important. So you can just see the moisture content is 0 at this point, the moisture content is maximum at the field capacity. The permanent wilting point does not mean there is no any moisture content, there is moisture content, but that moisture content is not available for the crop for its growth. So what is actually available is between this area, the field capacity and the PWP is the available moisture content. And even in the available moisture content, only 70 to 80% is available, readily available for the plant, and that area is given by the dashed line, and that is nothing but the optimal moisture content. So this red color arrow shows the amount of moisture content that is readily available for the plants. So you need to keep on. So this diagram very clearly shows the readily available moisture, field capacity and the permanent wilting point. So this is the optimal moisture content and this is the field capacity, and you can just see the moisture content drops when the crop is growing. Again you irrigate, the water content again comes to the field capacity, and the crop uses the water for its growth, it comes down to the readily available optimal moisture content, and again you irrigate, it increases, again it uses, again you irrigate. So this is the cycle that we have to keep on following for the entire crop period. A simple example will clearly illustrate this purpose. For how many days will you supply water to soil in order to ensure sufficient growth, sufficient irrigation for the crop if the field capacity is 28%, permanent wilting point is 13%, the dry density of the soil is 1.3 gram per cc, the effective depth of the root zone is 70 centimeter or 0.7 meters and the daily consumptive use of water for the crop is 12 mm. So we can very clearly see the field capacity is 28 here, it is 28, the PWP is 13, so the available soil moisture is 15%. So now we can assume that readily available moisture is 80%, so readily available moisture is 0.8 into 15, that is 12%. Therefore the optimum moisture content is 28 minus 12, it is 16. So we can very clearly see the field capacity at 28%, the PWP is 13, so the total available moisture is 15%, and in that 15 only 12 is readily available. So obviously the optimal moisture content is 16. Optimal moisture content is 16. So you have to vary the water content between 28 and 16. So whenever the water drops to 16, you again have to give water to the crops irrigation so that the field capacity, the moisture content comes back to field capacity. So it means that the moisture content will vary between 16 and 28%. So the depth of water that is stored in the root zone between these two limits. So that is nothing but how much amount of water you need to supply between these two limits. So it is gamma D into D divided by gamma W into field capacity minus optimal moisture content. So that will give us how much amount of water that you need to supply for each and every cycle. So now we know gamma D is not given in the question, but rho D is given, so we can find out rho D. So gamma D by gamma W is equal to rho D into G divided by gamma rho W into rho G. So that is nothing but rho D divided by rho W. So that is nothing but 1.3 divided by 1. So gamma D by gamma W is equal to 1.3, and we know depth of the root zone is 0.7, and we know the field capacity is 0.28. So please always remember, we should always put the field capacity or the PWP in terms of not in terms of percentage but in terms of fractions. So this value should be like, if it is the field capacity is 28%, then you should convert to 28 by 100, you need to put 0.28. So that will give us 1.3 into 0.7 into 0.28 minus 0.16. So that is nothing but 0.1092 meters, and that is nothing but 10.92 centimeters. So this is the amount of water that you need to supply for each and every time for the crop to grow. Now the total available water for the consumptive use 10.92 centimeter, but 1.2 centimeter of water is used daily for the crops. So that means in how many days this entire water will be used by the crop. So in 9 days this entire water will be used by the crop, 10.92. So you need to again and again irrigate the field after every 9 days. So this is the question. So coming to the second question, wheat is to be grown in a field having a field capacity equal to 27% and the PWP is 13%. Find the storage capacity in the 80 centimeter depth of the soil if the dry unit weight of the soil is 14.72 kilonewton per meter cube. If the irrigation water is to be supplied to the field when the soil moisture falls to 18%, find the depth of water required to be supplied if the field application efficiency is 80%. So there are two different questions are there in the same question. So one is they are asking us to find out what is storage capacity between field capacity and PWP, and what is the depth of water that you need to supply if you are going to irrigate the field when the soil moisture falls to 18% and the field efficiency is 80%. So these are the two different questions. So the first question is how much amount of water that can be stored between field capacity and PWP. That is nothing but the maximum available moisture. So directly we can find out gamma D by gamma W into D into FC by 100 minus PWP by 100. So I always said this value should be always in terms of fraction and not in percentage. So it is gamma D is 14.72 kilonewton per meter cube and gamma W is 9.81 kilonewton per meter cube. So this is where we all go mistake. So gamma W, the value is 9.81 kilonewton per meter cube. So 14.72 divided by 9.81 into 0.8, FC is 0.27 given in the question, and PWP is 0.13 that is given in the question. So 16.8 centimeter is the depth of water that is stored between FC and PWP. So in the second question, it is given that the irrigation is done when the moisture content reaches 18%. That is, it is well above, it is 5% above the PWP. So you are going to vary the moisture content from 27 to 18. So it is going to drop down to 18 when the plant grows. Again you irrigate it back, comes back to 27, and again it uses for its irrigation, it comes to 18, and again you irrigate, it will come back to 27. So this is the cycle that it is going to follow. So the moisture is allowed to vary between 27 and 18. So the depth of water required for irrigation is gamma D into D divided by gamma W into 0.27 minus 0.18, that is 10.8 centimeter is required for its growth. But what is the efficiency that you are going to see? 80% efficiency. So if you want the depth of water to be 10.8 in the ground, then you need to apply more because there is some losses. So the amount of water that need to supply is 10.8 divided by 0.8, that is nothing but 13.5 centimeter. So this is the total amount of water that you need to supply if you want 10.8 centimeter in the soil root form. A variety of problems that in this particular concept, like 800 meter cube of water is applied to a farmer's rice field of 0.6 hectares. When the moisture content in the soil falls to 40% of the available water between the field capacity, that is 36% of soil, and PWP 15% of the soil crop combination. Determine the field application efficiency. The root zone depth of the rice is 60 centimeter and assume the porosity is 0.4. So in this problem there is a slight difference between this problem and the previous problem. You can very clearly see that they have not given the dry density value of the soil, and rather they are given the porosity as 0.4. So we have to somehow use this value of 0.4 porosity in the problem to define the field capacity. So according to the definition, field capacity, the weight of water contained in the certain volume of soil divided by the weight of the same volume of dry soil. This is what we have seen earlier. So let V be the volume of the saturated soil and V be the volume of the voids in that particular sample of soil. Now the weight of water that is contained, if the soil is completely saturated, then it is VV into gamma W, and weight of the same volume of dry soil is V into gamma D. So FC is equal to VV into gamma W divided by V into gamma D, and that is equal to gamma W into gamma D into N, where N is nothing but the definition of porosity, volume of voids divided by the total volume. So we have a relationship between gamma D by gamma W is equal to N by FC. So if you know N, you can find out gamma D, or if you know gamma D and N, we can now find FC. So this is the relationship that you need to remember. Gamma D divided by gamma W is equal to N divided by FC, where N is the porosity. So since we have the porosity value as given as 0.4 and the FC value as 36%, that is nothing but in fraction 0.36. 0.36. So we have gamma D by gamma W is equal to 1.11. So we have gamma D by gamma W is equal to 1.11. So now the maximum quantity of water or the depth of water that can be stored between FC and PWP using the same previous problems, we can find out gamma D by gamma W into D into FC minus PWP moisture content. So we know the value of gamma D by gamma W, that is 1.11. It's nothing but 1.11, and D is depth, that is given as 0.6 meters, root zone depth 0.6 meters, and FC is 0.36 and PWP is 0.15. Therefore the depth of water, maximum depth of water that can be stored in the field content and PWP is 0.1514 meters. But in the question it is given that the moisture falls to 40% of the available water, irrigation is done. So the total available water is how much? 0.36. So we can see this in the very clear in the figure very clearly. So the FC is 36% and PWP is 15%. So the available moisture content is 36 minus 15, that is 21%. But the irrigation is done when the moisture content falls to 40% of the available water. So what is 40% of the available water? That is 8.4%. So 8.4% is it falls down to that level, then irrigation is done. So obviously the moisture content at that level is 15 plus 8.4, that is 23.4%. So the water moisture content is going to vary between 36 and 23.4%. So during this moisture content only the irrigation is going to be done. You can very clearly see now. So the optimal moisture content is equal to 15 plus 8.4, that is equal to 23.4%. The moisture content in the soil is allowed to vary between 36% and 23%. So the deficiency of water or created or the storage or that is being created during this water level is nothing but gamma D divided by gamma W into D into 0.36 minus 0.234, that we are getting it as 1.11 into 0.6 into 0.36 minus 0.234, we are going to get a value of 0.084 meters. So this is the amount of water that is required for the crop when the water level falls from 36 to 23.4. Now what is the volume of water that is required? You know the depth of the water, you know the area of the field, so you can directly get the volume of the irrigation that is required. So that is 504 meter cube. But actual water that you are supplying is 800. So output is 504 and the input is 800. So the efficiency is 63%, and that's what they are asking. Determine the field application efficiency if we are applying an 800 meter cube of water is applied. So in this particular problem is slightly different in this sense that you are not given the value of the density, rather you are given the value of porosity. Yes, that's all. These are the different types of problems. You can also solve the problems that are already given, and with this you will be able to solve all the questions that is there in the set of questions that are already given.